for the introduction. Thank you very much to the organizers, particularly Raul and Christian, for inviting me here. I was talking to Jack yesterday, or the day before, that I found surprising that you didn't cite your book, where your course was based on. I will not do the same. I will cite, it's not a book yet, but it's a set of lecture notes on archive. So lecture notes on, so this is in bracket because it's not the title of the course, on rough paths and applications to machine learning. So all of the material that, well, most of the material is that I will present today and tomorrow will be here. And so I co-wrote these lecture notes with Tom Cass, who is also, well, he's a professor at Imperial in our section. And yes, so you'll be able to find all the details there. So it's good that Terry gave his talk, his overview talk yesterday. So you already know more or less sort of things that I will talk about in this course. And of course, I have more time, so I will go more into the details. So a few warnings before I start. So there are some experts signatures in the audience. So I hope that even for you there will be occasional novelties. So I hope that you're not going to be bored to death during this 4 hours. And then for everyone else, which I assume is not familiar with signatures, yeah. So I hope that this will provide a motivation or a nice overview to get into the field. Second warning is rough. So there won't be much roughness in this talk. So this some rough paths in this case will be smooth paths rather than rough paths. But I will occasionally comment on how the different results could be extended to a rougher case. And the third point is that I will try to emphasize as much as I can the application, not really applications. I won't discuss specific applications, but I will try to highlight the links and the motivation of why the different results that I will present are relevant in the setting of data science and machine learning. So that is my focus, and that I'll try to keep in mind. Right, so there will be two parts. The first part will essentially be about controlled differential equations, which are a fairly general class of dynamical systems that are essentially the starting point of many disciplines, including stochastic analysis, control theory, and dynamical systems theory, of course. And I will use this prototype class of systems to introduce the signature, surprise, surprise, explain some properties, and then make a comment, which, you know, because I only have 4 hours, well, for you it's a lot, for present the material is not that much, but I will just give a sort of interlude to neural control differential equations, right? So these are more modern hybrid models that merge classical control differential equations with neural networks. But this will be just a sort of 15 minutes discussion. And then the second part will be about signature kernels. So this class of kernels that was mentioned by Jack in the end of his talk. Yeah, we'll explain some properties, how to compute them, why they are relevant in machine learning, and finally, which I hope to have enough time to get to that point, I will try to explain how signature kernel arises as universal limits, universal scaling limits of a randomized controlled differential equation. So I hope that this will be a nice way of joining the two sections at the very end. So hopefully we'll have enough time. Right, so the first part is controlled differential equations. Right, so I won't write all the details on the screen because I think this is not an undergraduate or graduate course, so so all the details are in the lecture notes. I will try to write the minimal amount of information on the screen, and then perhaps sketches of proofs a bit orally, a bit on the screen. But yeah, if there is anything unclear or you want me to slow down or accelerate, please say it. Right, so the type of differential equations that I will consider now are of this form. Okay, so dyt go to f of yt dxt. Okay, so just explaining each component of this equation in summary. So this equation needs to be started somewhere. So y0 belongs to some finite dimensional Banach space W, and X. So for me, X is going to be a path from 0, 1 into another finite dimensional Banach space V with some regularity, okay, with some smoothness property that I will specify as I go along the course. So for now, let's think about this as a smooth path. And then F is going to be a class of vector fields. So in particular, it's going to be a map that takes in an element of the second Banach space W and outputs a linear map from the first Banach space V back into W, right? And so you see that this equation is somehow, this definition of F is consistent with the equation that I wrote down, as it consumes, F consumes an element of the state space YT, and then outputs a linear map that interacts with X and brings us back to W, okay? So again, let's assume that is a smooth vector field, seems a smooth function, C infinity. But of course, if you are a stochastic analyst, then X will be usually a semi-martingale, and whilst if you are in control theory, you might be happy to assume just differentiability of your path, right? So that's why the least restrictive assumption are smooth, but then this can be changed, of course, depending on which field you are in. And of course, if depending on the smoothness or the roughness of X, some compromises need to be done at the level of F, right? So essentially, the rougher the driving path X, the smoother the vector fields F need to be in order to get well-posedness of this kind of systems, right? Again, so this link between F, the smoothness of F and the roughness of X is really important for unique existence and uniqueness, but I will not focus too much on these analytical details in this course, but I will try to give you true statements, but oftentimes will be easy statements, okay? So I will not focus on this interaction. Right, so this is one way of interpreting this kind of dynamical system. So the physical interpretation is that you have an external stream of information X that interacts with the physical system, right? And this physical system reacts to this external stimulus and produces a response, right? So that's that's essentially the meaning of this equation. And I usually think when I talk about this with non-experts, I usually give the example of an electricity signal that interacts with your washing machine and produces some angular velocity. Right? And so that's the angular velocity is the response, and the electrical stream is the input. Okay. So a different way, which oftentimes is a more convenient way of interpreting this equation, is as follows. So so we can rewrite it slightly differently in this way. So dyt is equal to f tilde of dxt yt. Okay, where f tilde now is going to be f tilde now is going to be a map from V into the space of linear maps, so endomorphisms between W and W. Okay, and so C infinity, and the relation between f tilde and f is simply that f tilde of V of W is equal to f of W of V. Okay, so you can see you can have this different interpretation that will produce the same answer. I think the nice one of the nice things about this interpretation is that if we assume that x is smooth, so x is smooth, so x is at least differentiable, what happens is that this equation becomes of the form dyt equals f x prime t yt et. Okay, and so in particular, this is if I differentiate rather than writing in this form, so like this is an ODE. Okay, so this is an ODE with a vector field. So this we can rewrite it as y prime t is equal to f that depends on t yt, and the f, the capital F here, it's a time dependent, or rather a path dependent vector fields that governs the dynamics of this OD. Okay, so that's this should be a more familiar type of objects. Okay, so that's the models that I will consider somehow throughout the course, and I think it's the most natural way of introducing the signature to, there are many ways, but one of them is trying to solve this differential equation via the classical Picard iteration. Okay, so this is not a necessary assumption, but it will simplify quite a lot the derivation from now on. So I will assume that f is linear. Okay, so f, to assume that f is essentially a linear map L from W into the space of linear maps from V to W. Okay, so that's I will mention when I will drop these assumptions, but without a further comments, this f is linear. Okay, so if f is linear, then we can run Picard iteration on this equation. Okay, and so this equation can be rewritten in integral form, right? So yt is equal to y0. This is equivalent plus 0, the integral from 0 to t of f of ys dxs. Okay, and okay, Picard iteration, it means that you start with an initial guess. So you have an initial guess y0 t, which is a path that is identically equal to the initial conditions. This is a constant path equal to y0, and then you iteratively replace this ansatz in your equation, and you get the next iterates. Okay, so y1 is of t going to be equal to y0 plus the integral 0 to t of f of y0 dxs. I'm not going to write all the details, but the f of y0 is constant, so this is just f of y0 times the increment. Okay, that's it. Now, if you repeat this iteration n times, you will get to the nth Picard iterate ynt, which will look like something like this, right? So we look like y0 plus you will get something like the sum, the integral from 0 to t of a function f that I will denote by f tensor k. So this sum runs from k equals 1, I guess, to n. F tensor k of y0 that I will define in a second. And so this is a function that acts on, so x is differentiable. So this is a function that acts on, sorry. This is not a single integral. So this is an iterated integral. So this is between 0 and t, and you're integrating over a simplex. So u1 to k less than t. And this map acts on the derivative x prime u1, comma, x prime u2, comma, dot, 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 x prime uk, and then you're integrating. So this is dt1 dtk. Okay, so if you run the Picard iteration, you get something like this, where this multilinear, well, it's not yet multilinear. Well, this map is defined in this way. So f tensor k of y0 is a map from, well, let's see, v times dot 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 times v, k times back into w, right? So to be consistent with the equation, that so it acts on a tuple, a k tuple v1 vk in this way. So it's defined recursively. So the easiest thing to do is to define recursively. So this is going to be f applied to f tensor k minus 1 of y0 that acts on v1 dot 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 v k minus 1. Okay, this is an element of w that then I can hit with f, and then I can apply it to the last v k and brings me back to w. Okay, so this is, you can define this map from the Cartesian product of vk times into w in this way, and this comes up naturally when running the Picard iteration. Can I do this? Yeah. Okay. So okay. So now this is a somewhat not super nice form. What you can do is that you can essentially rewrite this using the property of what we call tensor product. Okay, so the tensor product. So I'm not going to write too many details, but so if you have two vector spaces S and T, you can define an abstract space, vector space, which is called the tensor product space. In this way, so you have two vector spaces S T, and then you can define a new vector space S tensor product T. So here there is no, there are no matrices or indices. This is a more abstract kind of definition of the tensor product in this way. So the space is accompanied by a map, which is this tensor product map, which has the following property or universal property, is that if you take any other vector space U and any linear map phi, you can find there exists a unique linear map phi tilde such that this diagram commutes, right? Such that such that phi of little s t is equal to phi tilde s tensor product t. Okay, so this is a classical construction. It's a definition of the tensor product space. So tensor product space. And so using this construction, I said this definition, what we can do is that we can rewrite this map, f tensor power k y0, as a new map that acts on the tensor product of these x primes. So we can find there exists a unique f tilde tensor k of y0 that now it acts on the tensor product of the derivatives uk and gives exactly the same thing as the other one. Okay, but the point is that now this map is a linear map, right? So it's a linear map on this vector space, and so because it's linear and because the integral is linear and because the sum is linear, so I can essentially exchange things as I wish, and so I can rewrite this equation here as the nth Picard iterate in a more convenient form as follows. So this is y0 plus the sum k equals 0, k equals 1, I guess, to n of this new map f tilde tensor k applied to y0, acting on the iterated integrals, right? So acting on 0 ... t x prime u1 x prime uk d u1 d uk. Sorry, by the way, this should be du1, not dt1. Okay, so now I have a map that acts on this tensor. Okay, this is a k tensor. This object here now lives in V, belongs to V to the tensor power k. Okay, and if you put together all these tensors, that's the definition of the signature. Okay, let's the signature then S of the path x between 0 and t is going to be the collection of all this type of iterated integrals, right? So it's going to be something of the form 1, and then the integral of the x, and then the integral. So this is between 0 and 1, the xs 0 and 1, and then you have the double integral, so this 0, s1 less than s2 less than 1. So I guess t dx s1 tensor dx s2 and so on. Right. So if you put all of these tensors together, you get an object which is a series of tensors that lives in the product of all the spaces, of all the relevant spaces. So R, V, D tensor 2, and so on. Okay. And so a shorthand notation for this infinite products of tensor powers of V is this, right? So this is called the extended tensor algebra. This is a definition, and it will play a crucial role in this course. It is a very nice space. It has a lot of properties. Algebraists get very excited about this, and rightly so. I won't be hammering too much on the various properties, of this space, but I will need some of them, okay? In particular, what I will need is that I will need, so this is a priori, this is a vector space, right? This is space that is linear space, but it can be equipped with additional structure, and it can be turned into an algebra. And it can be turned into an algebra in various ways. The first, so we will see in this course 2 ways of turning this vector space into an algebra. The first example is going to be so, we need a product. So the first product, it will make this vector space a non-commutative algebra. T of V can be made an algebra. So the first product is, okay, so here is where the confusion sometimes arises. So usually for algebraists, the tensor product is this, right? This is what is called the tensor product of 2 vector spaces. And so if you have S and T being RD and RE, then the tensor product is the outer product, right? And it gives you matrices, which is fine. Now, what I perhaps erroneously will call tensor product on this space is a different product, but we'll also call it the tensor product, and we will not call this the tensor product. We'll just need this one from now on. So the tensor product on this space, and I will denote it by just a dot like this, is defined in this way. So you take 2 elements of T of V and A and B, and you get another element of T of V, which you call C, which is again organized by levels. So you have C0, C1, dot, 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 dot. Each one lives in the appropriate level, and Ci, so the ith level, is defined as the sum k from 0 to I of A k. So this is the kth level of A. Now, classical tensor product B I minus k. And so this, again, this is an element of V tensor power I. Okay, so essentially what you do is that you take 2 infinite series of tensors and you multiply them together, you get another infinite series of tensors, which the level I tensor is simply equal to the sum of the products of the corresponding levels of the inputs. Okay, so that's such that if you sum the degrees, you get the compatible degree. Okay, so that's it. Right. So you can, okay. So this a priori is a tensor product. You can define such tensor product on T of V, and then if you do that, then T of V becomes what we call the extended tensor algebra. Okay. So this tensor algebra is extended tensor algebra. Sorry, it's an infinite. Elements are infinite series. So they can be thought of as formal power series of tensors. Now there is another space which is a subspace of this one, which is denoted usually by T of V with only one bracket, which is essentially these are all the tensors in T double bracket V. Such that only finitely many elements are non-zero. Okay, so this is a subspace of T of double bracket V, such that only finitely many levels, only finitely many levels are non-zero. Okay. So in other words, to fix the ideas, this space can be thought as a power series of tensors. This space can be thought of as polynomials of tensors. Right? So you stop at a finite degree. Right. So then what's next? Just trying to set the scenes for So this is about the only bit of algebra that I will need, so bear with me. Of course, now it's a bit far, the machine learning, right? But we'll come back to machine learning very soon. Signatures are elements live in this space, and signatures are essentially paths, right? And this will be made more precise later on. But when you do machine learning, usually what you're interested in are functions on paths, right? Functions that act on paths. So using this type of setup, essentially the space that we will really be interested in is the dual space of this tensor algebra, right? So functions that acts on elements of T of V, in other words, functions acts on signatures, right? So the dual space, we will be interested in the dual space of T of V, so T double bracket V star. This is the dual space. And so there are several things that one can say about this dual space. What will be important for us, it's going to be a basis. Okay, so a way of indexing elements of this space. Okay, and it's very easy to construct a basis for this space. You start from V, right? So basis construction. So you start with V, and V is equipped with a base with, let's suppose that V is d-dimensional. It's equipped with a basis E1 up to ED. Now, if you have a basis for V, you also have a dual basis, right? E1 star, ED star, such that EI star, EJ is just delta IJ. So that's a dual basis for V. Now, if you have a dual basis for V, you can construct a basis for V tensor power K, okay, which is simply going to be given by all tensor product of K tuples of basis elements of V, right? That's this IJ, I sub J runs, belongs in 1D. Oops. And again, this can be dualized easily like this. Okay, so this is so we have a dual basis for the kth tensor power of V. And then you can use, the bilinearity essentially. You can extend this basis to the whole of T of B. Okay, so extend to. Actually, the easy thing to do is to first extend to T of B star by linearity, because this is a linear space in V, and then show that essentially this space, these are details, this space is isomorphic to the space that we care about, T of V star with the star outside. Okay. So in other words, usually people in some communities refer to this type of elements here. No, I don't want to get in trouble, as words. Okay, why words? Well, because if V is d-dimensional, you can think of V as the space spanned by D letters. And then if you look at V tensor K, you can think of it as the space spanned by words in these D letters of length K. And if you think of the tensor algebra, which is the direct sum of all these levels, you can think of it as the space spanned by all words. in these letters, right? So it's a convenient, is this clear? It's a convenient way of think of this way of indexing basis elements of these abstract spaces using the analogy of words. Okay, so I will refer to this as words. And this, for example, is a word of length k, with k letters, and these letters are in the dictionary. Well, I guess the words are in the dictionary, but in the alphabet of these D letters. That's it. Okay, so that's it. And so, of course, this is convenient because then if you have the signature, which is an element of this space T of V, I can extract individual coefficients of the signature by simply contracting this tensor with a word. Okay, so if I take any word, E1, like this one, for example, E1 star, EIK star, what I can do is that I can act on the signature of a path X and extract the corresponding coefficients in front of this word, right? So this would be a scalar, which will correspond to the iterated integral, the corresponding iterated integral, okay? So maybe I should write it down. So this is equal simply to the iterated integral, U1 dot UK between 0 and 1, say, where the elements of the path that I want to consider are specifically indexed by this word. So dx U1 coordinate I1 dot dx UK coordinate IK. Okay? Yes. There is no trees here. It's just words. You can get trees, but yeah.
I asked to repeat main steps from the beginning. For example, we defined controlled differential equation. Yes. Then we write solution. Yes. And for solution, we need tensor product space. Yes. And so on and so on and so on. Because somehow I lost the big picture.
Sorry. Okay, so you have the differential equation. You run a Picard iteration. If you run the Picard iteration, you get an expansion, right? The nth Picard iterate, yn, it can be written as an expansion, Taylor expansion in terms of these iterated integrals. Now I somehow forget about this equation, and I just look at these iterated integrals. I just put them all together, and the collection of all these iterated integrals is what we call the signature, which is this, right? Which naturally lives in this space here, which is the product of all the tensor powers of the underlying vector space V. And it can be equipped with the product and made into a non-commutative algebra, which we call the tensor product, defined in this way. And we can index elements of this space using words. That's all I've said.
Last point, we try to define basis in which we express solution.
Well, this is a basis of the tensor algebra, right? That's all. And just making an explicit is one basis. It's a canonical basis of this space, so that it will be easy to select specific elements of the signature by simply looking at the specific basis element. It's just somehow an indexing notation that should clarify what comes next. And there is a way of thinking about these basis elements as words, because it's a convenient way of thinking the literal word, like, lexicographical words. That's
this single basis vectors, it's canonical basis.
Yeah, Yes.
And can you please also say what should we expect next 15 or 30 minutes? Where do you go?
Right. Yes. Sure. Yes. And so where I go from now, so I will not talk about algebra much anymore. So so this is a good point to get to properties of the signature. So for the next few minutes, I will talk about the signature and highlight some of its properties. And there are two classes of properties. Some of them are more analytical properties. So I will start with those. And then I will talk about more algebraic properties. For analytical properties, there are three main analytical properties. So the sampling invariance, factorial decay, and uniqueness. So let me explain why these are relevant in the setting of machine learning. So invariance. So if you're doing computer vision, for example, usually what you'd like your model to capture are rotation invariances, right? So you want your dog to be classified as dog, no matter how the picture is rotated, right? So you would like to have a neural network, for example, that has an invariance to rotations. Okay? So invariance to actions of a group of an object, so group actions of an object on data is important. Okay? Now in computer vision, the rotations are and translation are sort of easy to deal with because these symmetries, they live in a finite dimensional group. And so it's not too complicated to build invariances to this nice type of symmetries. Now on path space, there is a specific group of actions that act on paths, which is given by reparameterizations. Okay.
Yeah, I'm sorry to interrupt you.
Yeah.
I just try to understand. We start with relatively simple differential equation.
Yeah.
Or maybe it's not simple and I miss something important. But then we come to relatively complicated tensor product spaces. What would come? Do we have some other methods maybe to solve this initial differential equation? So I try to understand what do I miss? Why from this relatively simple equation we come to this not so simple theory?
Picard iteration. That's it. Take your ODE driven by control. You expand it with using Picard iteration. You get a Taylor series in iterated integrals. So the I'm talking about these iterated integrals. They're a natural object that appear when you want to solve this type of control systems using Picard iteration.
And this differential equation was depending on time and x1, so on many x, or just...
Yeah, it's like an SD, right? If you have an SD, like, I don't know what's your background, but if you have an SD, you can drive the differential equation by a d-dimensional Brownian motion, right? So that's a type, is an example of this general form of control differential equations. So for SDs, the path that controls the dynamics is Brownian motion. But yeah, that's an example.
Okay, thank you.
Yeah. Oh, wow.
Okay.
Good catch.
Still alive. So, sorry, it's a very basic question, but because I was trying to write on what you did before, I understand, I think it was the page before, I understand when f is linear, how you get, all these terms, I mean, all the, the dx and so on, right? All the elements of the signature. But when f is not linear,
yeah,
is it obvious that you can always write it that way?
So when f is nonlinear and
Not even before.
Yeah.
By really at the beginning. I mean, when F is linear, it's clear, you know.
Yeah, so when F is nonlinear, essentially what you can do is that you can run the same Picard iteration. So F, if it's nonlinear, it needs to be smooth. I mean, it has to have some bounded derivatives up to a certain order, right? So, if that's the case, then essentially what happens is that this, instead of having a multilinear extension of the underlying F, you will have derivatives. Exactly. So you have the actual Taylor expansion where you have derivatives of F that appear. Yeah. But of course, most of the time you can't really use the full series, right? Because things might not converge. So in this case, this is nice, but yeah.
Thank you.
Yeah. Right. So invariances. So you know, simple example, simple picture that. You can find a better one in the lecture notes, but I'll try to repeat it here. So for example, you are in the situation where you want to recognize this picture, okay, which is an 8, I think, looks like an 8, which is, I mean, this is a good example because I'm writing on the board, moving the pen, this two-dimensional path, right, two-dimensional curve, indexed by my hands, right? And I'm going through it like this. So this is a two-dimensional oriented curve, which looks like an 8. And it looks like an 8 no matter how fast I go to the screen. I go through the screen, right? If I go very slowly at the beginning and then I accelerate at the end, or I go very fast all the way through, or I go fast at the beginning and then I decelerate at the end, this will always look like an 8. No matter what kind of sampling frequency I use to construct the curve, okay? So if you're doing hand written digits recognition, for example, you would like your model to be invariant to sampling frequencies, right? So how fast you go through the curve. Mathematically, this way of reparametrizing the paths are called, you know, we can define them as reparameterizations. So these are a group of functions that map an interval, you know, AB to an interval CD, right? Which are continuous, surjective, and increasing. Okay, so this is a group of reparameterizations. Okay, so that and what you can do is that you can, you know, if you have a path, let's call this path x of t, you can reparameterize it x tilde by composing it with the reparameterization, right? So this original x will be a path in AB, and it will be reparameterized according to this function into a path on CD. Okay, and essentially what the signature does, so this is somehow a lemma, is that the signature doesn't see this. So the signature of x, so let's call actually this x superscript lambda to indicate that it is reparameterized by lambda. So the signature of x subscript lambda is equal to the signature of x for all lambda like this. Okay? So in other words, the signature is invariant to reparameterizations. So that's sometimes this is a useful property to have. I'm not so the proof. So this can be proved in different ways. Just a sort of sketch of the proof is as follows. So what you do is that one way of proving it is by induction. Okay, so you prove it by induction on the levels. And essentially what you do is that at each step of the induction, you essentially just use some elementary measure theory. And so the main observation here is that you know, if you have an integral of, you know, of a function of time f of t, and then you are integrating this against dx t. Let's suppose that this is the ith coordinate of the path x. Okay, so this integral here, in a measure theoretical way, at least if x is of bounded variation. So this is actually something that. So let's assume here, where can I write it? So x of bounded variation. So I assume that it's clear what bounded variation means to everyone. If x is of bounded variation, then essentially what you can do, you can interpret this dx as the integral of f of t against the measure mu xi of dt. Okay, and this measure is just the the Lebesgue-Stieltjes measure associated to x, right? So this is just the measure that mu xi of an interval AB. This is just xi at B minus xi at A. Okay, that's it. So essentially, this integral is just a classical measure theory Lebesgue integral. Okay, where the measure is like this. So you can use measure theory to prove this statement. It's a very simple thing. Now, what if path x is not of bounded variation? So that's, I think, it's an interesting technique which is used quite often in rough analysis in general. In more in general than what I would explain now. But so if you have x now that is of finite p variation, so finite p variation with p between 1 and 2, not including 2. What you can do is that you can extend these results in the following way. So you know that this result holds when x is a finite p variation for p equals 1. And then you can use these two facts. So you can use the fact that this map, so the map between paths of bounded p variation. So this is just a short way of writing paths of bounded p variation. So the map that takes two paths of bounded p variation and give you another path of bounded p variation, which looks like this, fg, and this gives you the integral of f dg. So this is the Young integral. This is continuous in Q variation. This is continuous in Q bar for any Q strictly bigger than P. So the first step is to, the integration map that integrates a path against the other in Young sense is continuous in Q variation. It's the first thing. And then the second thing is that if you take C1, so these are the paths of, sorry, I'll go quickly here, but if you take C1, so these are the paths of one variation for which we know that this theorem is true, and you take the, you close it in Q variation. Okay, so this is the closure of C1 in Q variation. This space contains CP. Okay, so in other words, if you reformulate the statement, the paths of bounded one variation are dense in the space of paths of bounded P variation in the Q variation topology for any Q bigger than P. Okay, so now if you put together these two facts, the continuity of the integration map, which is essentially the integration map is what you need here for this statement because signatures are just integrals, and the density. So you have a continuous function, and then you have a class of paths over which this continuous function satisfies a property, and this space of paths is dense into another space. Therefore, this function needs to satisfy the property also in the other space. Okay, so you combine the continuity of the map with the density of the space where things hold to get the results. So this holds, essentially, this result holds for any paths x in CP for P between 1 and 2. Okay, using this density argument. Right. So maybe a quick comment. So if P is 2 or bigger, then you are in a rough path setting. Okay. So if P is equal to 2 exactly, you are in the sort of Brownian motion world. And then if P is bigger than 2, you start to have rough paths. Okay. All of these things, including the solution theory for the original control differential equation, can be extended to this higher, rougher settings if you have the right notion of integrals. And this is what rough path theory does, right? It allows to define a sensible notion of integrals for paths that are rougher than just of finite p variation between 1 and 2. And then once you have an appropriate notion of integrals that satisfy all the properties that the classical integrals satisfy, like integration by parts and all the rest of it, then you can somehow extend all of these nice things to that, right? But the core problem there is how to define the integral if p is higher than 2, okay? And we're not going to see that in this course, but you can do it. I mean, people could do it, and now we learned how to do it, and we can use that and do the same type of things for rougher signals. Okay, but yes.
Yes, I just try to understand what I do not understand. Yes, and I have 3 questions. Control differential equation. Actually, whole life I was working with elliptic PDEs. Yes, and I'm not expert. I mean, I saw this equation which you showed. Can you, in few words, say what is the problem, where it's difficulties in this equation? This is first question. Second, Picard also, okay, it's iterative methods. I heard this word, I saw the theorem, but I do not have deep, maybe I forgot, what are the difficulties in this method? Do we now, what we are doing now, do we develop a new method, or we investigate properties of this equation, or?
Right, so my goal is not to solve an equation, right? My goal is to introduce the signature and explain some properties and then do machine learning.
I'm sorry, you said introduce signature, but I'm stuck already a little bit earlier. What is signature? Is it set of solutions or?
Yep. Yeah, of course.
I mean, I'm sorry but I think in a very, very broad sense, part of the things that you can do with the theory is like uncertainty quantification for this kind of control differential equations. Because you have a very complex, difficult input, which is x, path driving your equation, and you want to understand how does the solution behave in terms of x. How sensitive is it? How, if you perturb x, if x is random, and you have to deal with the fact that standard solution theory, the whole point of rough path analysis, leads to solution maps which are not even continuous. So you have no stability, it's not well posed. And therefore all the normal methods we would use for uncertainty quantification fail unless you somehow stabilize the equation. And maybe this is a way to relate more to where you are coming from.
But yeah, what Christian is saying is that if you have suppose you're from which stochastic analysis or okay, so well if you take an SD, right, the classical SD mu yt dt plus sigma yt dwt, right? It's an SD. Two things. You can look at this equation as a map from the Brownian path to the solution of this thing, right? So it's a map from paths to paths, right? And as Christian was saying, if you look at this, if you do analysis on this map in a naive way, using, for example, things like a uniform topology on paths, you don't get continuity. So this map is not continuous. And this is actually not true even for if W is smoother than Brownian motion. The continuity is sort of lost a priori. If you use, whilst if you interpret this, if you rewrite this function from paths to paths in the same way as I wrote it before, so as a function or acting on the iterated integrals of the driving path, then all of a sudden you somehow reinstore continuity. So one motivation for doing this, seeing this from an iterated integral standpoint is to get continuity of this path to path kind of map. The second motivation is perhaps from a numerical standpoint. If you look at the Taylor expansion at order 2, that would give you a higher, a second order Euler scheme for your differential equation. So these signatures are ways to obtain higher order numerical solvers for SDs or CDs of this form. So if your focus is to solve differential equations, then one motivation would be that, right? To build the higher order numerical schemes for these equations. Does this answer your question?
We are now constructing high order numerical schema.
You could do it, right? I'm not going to do that because this is not my focus. But if you look at the Taylor, Picard iteration, and you stop at order 2 and you do things locally, that gives you a second order Euler scheme for your control differential equation, where you're not using just the increments of your Brownian motion, but you're using also the Levy area, right, over the given interval to construct the next step. So it converges faster than if you just use the increment.
But what is your final goal for this tutorial?
For this tutorial,
Yes.
it's to explain how signatures can be used in machine learning.
Okay.
So I need to first explain what signatures are and what are the nice properties, and then I will comment throughout why they're relevant in machine learning.
Thank you.
Yeah. Right. So the second analytical property is, what did I say? It's a factorial decay. So what does this mean? That of course, if you want to use signatures on a computer, so you have an input path, an input digits, an input time series. You want to compute signatures. If you do that, you have to. You will not have an infinite capacity, an infinite memory capacity, right? So you need to truncate at some level. So you have just finitely many iterated integrals, and what a property that the signature has is that the coefficients, the amplitude of the coefficient decay very fast, right? So the higher in the signature you go, the smaller the amplitude of the coefficients become, right? So it decays factorially fast. So things become very small, very fast. So in other words, if you neglect higher orders of the signature, you don't lose too much information. So you can truncate safely. Now, this is a risky statement because it might be that the function that you want to approximate is exactly captured by one element in level 100 of the signature. So that's the exact function that you want to approximate, in which case, what I've said is irrelevant. But if, for example, you want to solve differential equations, well, you can construct a Taylor expansion or an Euler scheme that uses just the first 3 terms of the signature, and that that discarding all the other infinitely many terms, you will not make a big error, right? Because you have this very fast decay in the amplitude. So the error that you make by approximating the differential equation using the signatures is going to be factorially smaller the more terms you include. Yeah.
Signature is a vector, yes? Redefined, or it's set, or how to say?
The tensor. It's a series of tensors, yes.
Series of tensors, yes?
Yeah.
I mean, I see definition here. I listen, of course, and it's written here. So I thought it's like vector which belongs to tensor product space, no?
Yeah.
Yes?
Yeah.
So it's, okay. And then it's bricks from which I construct solution later on. Can I say like this or not?
Sorry. Can you repeat the question?
Signature is a set of bricks from which I construct later on solution, or not?
Yeah, I mean, you can say that. Yes, I think it's in a vague way. Yes.
Okay.
I think so.
I mean, believe me, signature I never heard before, so I have.
Okay.
Maybe.
And you know, there was a poster, at least one poster talking about signatures, I think, right? It's yeah. Even this, well, anyway, yeah. So let me write down the this one. So what is this factorial decay? So yes, another lemma. So if I take the signature of a path X and I look at level K, and then I take the norm in V tensor power K. So this is bounded above by what? By the one variation of the path. Sorry, one variation of the path to the power K divided by K factorial. But sorry, I'm not writing all the notation, right? But so this is the one variation of the path, and this is the factorial decay. So things decay very fast. Right. How do you prove this? Again, a sketch of the proof. So if you have a path X bounded variation, what the steps of the proof are as follows. So you can reparameterize. So you can find, this is either you trust me or you try to prove it as an exercise. You can find the reparameterization of the path X, call it lambda. So there exists a lambda that maps X between 0, 1 to 0, L, where L is the one variation, is the length, right? So it's called also the one variation of the path. There exists such a reparameterization such that, if I reparameterize X by lambda, so X superscript lambda is Lipschitz continuous. So it's Lip continuous. So in other words, I can reparameterize a path to be valued in an interval that is 0 its length, with the property that this path is Lipschitz continuous. Okay. Now, if you have a Lipschitz continuous function, this is also absolutely continuous. If it's absolutely continuous, you can use your Radon-Nikodym theorem to prove that it has almost everywhere a derivative in L1. Okay. And now, if this path is differentiable, you don't need to do all that, right? But if the path is bounded variation, you need to reparameterize into a path that is at least almost everywhere differentiable. So it has a derivative. And now, if it has a derivative, what you can do is that you can simply look at the signature of the reparameterized path at level K, take its norm. And so this is going to be equal to, well, let me write it. So this is equal to the integral U1 ... UK less than L of X lambda U1 X lambda U1 prime. So it has a derivative. Tensor tensor X lambda UK prime du1 duk. I put a norm here. Now I can put the norm inside and put an inequality here. So this is less or equal than this norm. Okay. And now this is actually equal to the integral, and now I can split the norms, right? So this is I have a norm X prime U1 lambda, and then ... norm X prime UK lambda, and now du1 duk. Okay, but now because x lambda is Lipschitz continuous, I know that the norm of its derivative is bounded by 1, right? So this is just less or equal, writing in here, this is less or equal than, you know, the integral over the simplex. Let me rewrite it because now it becomes important. UK less than L du1 duk, right? So this is just the volume of the K simplex, right? Which is equal to L to the power K divided by K factorial. Okay, now L is the one variation, right? So, and the signature is invariant by reparametrization. So we know that the signature of X lambda is the same as the signature of X. So that's the result, okay? Okay, so that's the, okay, so then the final property, analytical property, is something that is quite, of course, quite important, and this should be emphasized, so uniqueness. So if, you know, if the message so far is that the signature is a good way, or is perhaps a good candidate to represent paths, instead of looking at paths, you can look at the signature of the path and then do machine learning with it. At least what one would require is that there is a one-to-one correspondence between the path and its signature, right? Because that, so it's, in some sense, you would like to ensure that the signature is faithful. It's in one-to-one correspondence with the path. And this, if you do things in a whole generality, this is not true. Okay, so the signature, if for a given path, the signature is not unique. And one example is reparametrization, right? So if you take one path, you reparametrize it. These are two different paths a priori, but they have the same signature. So that's already a problem. I will come back to this later on, but there is a good way of ensuring uniqueness of signatures, which is given by the following fact. So if you take rho, right? If you take rho to be a map from 0, 1 to 0, 1, which is monotonically increasing, monotone, just monotone, can be decreasing, strictly monotone. So either monotonically increasing or decreasing, and then you consider the paths of this form, so x t to be of the form rho t x t minus. So these are all paths that have one strictly monotone coordinate. Okay. Then in this case, if this path is of this form, then you know, I mean, you have there is a theorem that tells you that the signature of x is equal to the signature of y. So this, I guess, is then. So if you have a paths of this form, signature of x is equal to the signature of y if and only if x is identically equal to y. So by including one monotone coordinate in your paths, you have reinstored the uniqueness. Okay. Yes. Yeah, that's an example. Yes. So exactly. So if for example, if it suffices to it suffices to take x composed with rho inverse. Rho inverse exists because this is monotone, and that's time. So essentially, the first coordinate becomes time. Yeah. So, and because the signature is invariant to reparametrization, we can think of the first coordinate to be time. Yes. We can think of this monotone coordinate to just be increasing because you just multiply x by x or by minus x or vice versa if it's decreasing. So we can, without loss of generality, think of it as increasing and think of it as time by reparametrizing in this way, right? So the proof works in this way, exactly in this way. So without loss of generality, I can consider x to be of the form t, as Jack said, txt minus, so this is in Rd, right? Let's suppose that this is in Rd, and this xt minus is in Rd minus 1, just to fix the ideas, and yt is the same, right? Yt minus. And now, so if you do that, then what happens? So, of course, if the paths are equal, the signature will be equals, right? So this direction is easy. Now, if the signatures are equal, then what happens? Well, actually, I don't even need to all the terms of the signature to be equal. I just need to look at the specific class of, well, a specific collection of terms in the signature, which are of this form, right? So if the signatures are equal, so this is what? This is this direction. Then I will have equality of this term, so integral of t k plus 1 dx minus t, and t k plus 1 dy minus t. Okay. Sorry, I forgot a very important part of this lemma is that for it to be true, I also need the paths to be started at the same point. So plus, I need the condition that x at time 0 is equal to y at time 0. Because another thing of the signature is that it's also invariant to translation. Okay, so I need to ensure that the two paths are starting at the same point. If they start at the same point and they have a one monotone coordinate, then I have this equivalence. Sorry, yeah, forgot that. Okay, so if we assume that the signatures are equal, then in particular, these terms, this type of terms are equal, right? So for any k from 0, 1, all the k's. Okay. Now, if these terms are equal, then what you can do is that you can use just integration by parts. So where are we? Let's suppose that we're integrating between A and B. You can use integration by parts to get something like, you know, what? B minus A what you get, hold on. Well, you essentially you will get something of the form integral. So you get k plus 1 integral A to B tk x minus t dt equals k plus 1 ab tk y minus dt. And then you have the constant terms that cancel out that I didn't write because there are 4, so I don't want to write them down, all of them, but they cancel out because of this condition, right? So this condition is something that allows you to cancel out the constant terms that arise by integration by parts there. So you end up with this equality here, so you can just remove this part. And so here you see that what this equality tells you is that this path, so the path x minus y minus, so if I bring this part to the left-hand side, I get that this path, when I integrate this path against t to the k, I get 0. And this is true for all k. So in other words, this path belongs to the orthogonal complement of all the polynomials, right? And in L2, right? So this is an L2 inner product. And so because polynomials are dense in the space of continuous functions, or at least on AB, well, these paths must be equal almost everywhere, right? So this path here must be equal to 0 almost everywhere. because when tested against polynomials is equal to 0, right? And polynomials are dense. So this must be equally 0 almost everywhere. And because this path is continuous, it must be equal to 0 everywhere. So that's it. So that's, I think it's a nice way of seeing uniqueness for this type of paths. Yeah? Yes.
Sorry, just for A was equal to 0 and B was equal to 1 here. Or
yeah. But this is arbitrary. Yes, sorry. Yeah. Okay. So at least for this path, the signature is unique. I will come back to this later, to this uniqueness. But for now, yeah. So the next part is about algebraic properties. And in particular, algebraic properties will enable, at least one of them, it will enable us to do computations, right? To compute signatures on a computer in an efficient way. Because a priori, these signatures are, iterated integrals. So if you'd like to implement them in practice on a computer, it doesn't seem a very easy task to do, right? But thanks to the chance relation, which is the next property I would like to mention, we can compute them efficiently, more or less efficiently on a computer. So let me give you an example. So suppose that I have linear paths, right? So suppose that I have a linear path, which for some reason I always get wrong. So let me xt xa plus t minus a, b minus a, xb minus xa. Okay, so this is a straight line. So this is a linear path in RD, right? So let's suppose that I'm in RD. I have a point xa, I have another point xb, and I just have a straight line from A to B, okay? So if I want to compute the signature of this d-dimensional straight line, then very simply, you can do x signature of x. This is differentiable, right? So I can just evaluate a level k. I can just evaluate the iterated integral of the derivative. But now what is the derivative of this? This is just, I can put it outside because it's a constant, xb minus xa divided by b minus a. And I guess I need to multiply, raise to the power k. And then I have an iterated integral of the usual du1 duk. And this is between a and b. Okay? So now, again, the volume of the simplex is just b minus a divided by k factorial. Hello?
Didn't you say that x was in RD? So how do you interpret the power there?
Yeah. Yeah, thanks. Then this is just xb minus xa tensor k divided by b minus a to the k times b minus a to the k divided by k factorial. Right? And so I can cancel out these two terms, and what I get is just the kth power of the increment divided by k factorial. Okay? If I put together all the levels, then I simply get that the signature of x is equal to the exponential. And this is the tensor exponential. So essentially just the classical exponential, but with the powers replaced by the tensor powers Exponential of what? Exponential of the increment, xb minus xa. So in other words, signatures of straight lines are very easy to compute. They're just exponentials of increments. Christian, if you... Yeah.
Sorry, just one thing. When you write Sx, so the signature of x to the k, because in the integral, right, I have dx u1, dx u2, dx u3, and so on, right?
Yeah.
But then, okay, so if I look at dx u2, u2 is greater than u1.
Yes.
I would write x u2 as x u1 plus t minus u1, right? So the b would be u2 and the a would be 1.
Yes, but in this case, because x is linear, and so in particular is differentiable, you can rewrite dx as x prime dt. And x prime is just the increment.
Okay.
Or no matter what.
Otherwise, all the a, I mean, I would have, I couldn't factor it out completely. I would have all the terms x minus xu1. All the dxu1, dxu2 that are inside.
Yeah, but this, if you take the derivative of this path.
Yes, but if I look at the xu2 term, for example, inside the integral.
Yeah.
Because u2 is greater than u1.
Yeah. Yeah, absolutely. And this is, so exactly. So that part remains, right? This is this part. So that part is there. It's just that if you take derivative of this, you will have xb minus xa divided by b minus a, which is a constant.
Yeah, but actually my point was that the b and the a change every time, would be u2 and u1 every step.
No, because this is time, right? So this path is really, the only variable is time. So these are constants that are fixed, xb minus xa. Just that the linear, yeah.
Sorry,
Right, so if you, yeah, sure, yes, thanks. So so the signature of linear paths is easy to compute. And now if you have a time series, right? So usually on, in practice, you will have a time series of this form. Right, so you will have, a time series is just the concatenation of many pieces, many linear pieces. I mean, one way of seeing a time series is just a piecewise linear path, right? Concatenation of x1 with x2 with x3 and so on. So if you have a piecewise linear path x, which is obtained by concatenating linear pieces, so x2, xk, so this by this star, I mean literally concatenating the path with themselves, then the lemma that I will explain, I will write down in a second, will allow to write signature of this concatenation as the product of the individual signatures. Okay, so the signature of the concatenation of these k paths is equal to the tensor product of signatures of the individual pieces. And now, because the individual pieces are linear, we know that the signatures are just exponentials, right? So this is just going to be the exponential of the increment of the first piece that I'll write dx1 for simplicity, dot to dot, exponential increment of the last piece, the xk, right? If you have a time series and you want to compute the signature, what you do is that you compute the signatures over the individual linear pieces, use it by exponentiating, and then you do a tensor product of the exponentials, and that will give you the signature. Now, this is thanks to the chance identity that I will introduce after the break. And as a last comment, this is this way of computing signatures is the way that is used in all the Python libraries that we have. So under the hood, this is how we do it. Okay. Yeah, I think it's good to stop. Yeah.